About a company that we formed in January of this year. So the company is brand new, but the entire team are veterans with very substantial experience in the power electronics industry. And we're going to talk about I'll talk about how we can leverage a existing technology base that spent 25 years developing bipolar junction transistors in the silicon carbide space, and about how innovations in the last 2 years have made our company possible and an entirely new class of devices with the benefits that are obvious from if you just look at our PowerPoint. The most obvious benefits to me, at least for NASA, are the fact that rad hard, lower mass, lower volume, much higher efficiency, much longer field life. And in general, we provide the required drivers and the systems and circuit design in order to meet customer needs. So this is what we're doing. We have very good reason to believe that we can do this. Our main needs, really, we got three. One is customers. We are in discussion with 2 customers right now, one in the US and one in Europe, regarding their needs. And when we say high power, we're looking generally at anywhere from 1/8 of a kilowatt up to about 1.5 kilowatts. So that's what we consider to be high power in terms of the markets that we're addressing. Why silicon carbide? I don't know if everyone knows about silicon carbide, but in case you don't, it's got a tremendous heat capacity. There's only one figure of merit which is absolutely vital, which is the temperature it can operate at. Silicon carbide CPUs, memories, and sensors are currently operating in the laboratory at 500 degrees C. Silicon cannot approach that. In terms of radiation tolerance, in both of the most important measurements, in both gamma and single events that happen, the silicon carbide gives us the ability to provide 1 to 2 orders of magnitude improvement over existing technology. And in terms of NASA space applications, the initial application that we're working on is a pulse power, and that would focus on applications such as either disintegrating junk in space or giving it a push so it goes down the atmosphere and degrades in the atmosphere, solving a pretty major problem in low Earth orbit. Just want to tell you the difference between our transistor and the legacy solution for high power. The legacy solution is an IGBT, insulated gate bipolar transistor, which is a combination of a BJT and a MOSFET. And the only thing that I think is really important to understand in terms of space at least is the polysilicon gate gets hit by a proton, high energy proton. The entire IGBT disintegrates. We don't have a polysilicon gate. We have no gate oxides. And I can discuss some aspects of the technology, but we have our technology team here, and at the impact tables, we'll be very pleased to discuss the technical details with you. And a key point, which I should have mentioned a bit earlier, our team wanted to make an impact. We've been talking for about 7 years in terms of what can we do in the high power arena, and the technical developments in the last couple of years is what enables us to do what we want to do. Here's an overview of what silicon carbide can do, and it should be very clear. Silicon carbide is very new. The initial commercial products only came out in 2010. It's gaining some market traction, but it'll probably be 2025 even before there's $1 billion in silicon carbide power modules being sold. So it's a rapidly emerging market. 78x growth in the last 10 years. I'm going forward a couple of 2020, sorry. But 78 times growth. The legacy insulated gate bipolar transistor, 4x growth in the last, in the 10 years from 2010 to 2020. Oops. This is another slide. I'm really talking to the growth. This is the power modules. We'll be selling silicon carbide power modules because that is what a customer wants. They don't want a chip at this point. Our chip enables us to do many very useful things like solid-state transformers are enabled, advanced pulse formation networks for lasers and other applications are enabled. But fundamentally, the customer wants a solution, which is a power module, not a chip, which is a problem. Why now? The technology in 2017, 2018 enables us to do what we want to do. We've got the ability to deliver first test devices to customers with $1 million using the lab that we're cooperating with. That's the KTH Institute in Stockholm, Sweden, which is the source for most of the advanced wide bandgap technology in the world. And last but not least, we've got significant market potential, and we think that we've got a realistic timeline and plan to grow to 100 million revenue in 7 years. Oops. Hey. Okay. So this is an example of a prototype. Was done last year, beginning of last year, 15 kilovolt device up to about 10 amp current potential. The key point here is implantation free. We want to commercialize a brand new manufacturing technology, which is using epitaxial doping. That has been used successfully at the KTH Institute, and we have good reason to believe, and happy to discuss at the impact tables exactly why we think, first, it'll be extremely valuable to commercialize in the United States, and why it enables a number of very desirable features that hot ion implants simply will not give you. So our go-to-market strategy, in fact, our marketing strategy is fairly simple. Talk to large companies, talk to them about what we can deliver, what do they need for next generation systems, and then design for the customer. The extension of that is for the first 2 customers we're talking with, there's a whole range of other companies and applications for exactly the same chips, but packaged into different power modules depending on the system solution. So this is our first product. The main takeaway is it's a low voltage, which is great for us because at low voltage we had very high current gain in a switching application. At 200 volts, we're looking at somewhere between 250 and 350x current gain, which gives us very tight control and very fast switching when we need it. Now this application, as you can see, you want 10 to 100 pulses a second, so the duty cycle is quite low for the actual pulses. This is our second product for European customer, main grid, microgrid type of focus. It actually is to replace an existing power module with a power module that's silicon carbide. It's lower mass, smaller volume. A single chip solution provides a lot of benefits versus multiple chips. And then last but not least, in volume, the manufacturing cost will be considerably less than it is with an IGBT. This is our team. We've got a lot of experience combined both in commercializations of technology. Bo Hammerland, who is here today, and Sam Ochi, who is here today. Bo has started 11 companies in the silicon carbide space, sold 2 of them. The other 9 are still operational, but other people are managing them. He's a serial entrepreneur, also a technologist, worked, for example, at Bell Labs, and then subsequently got a degree at KTH Institute, which is also our partner. Sam Ochi has got about 100 commercial ICs in production. He either designed them or managed the design and contributed to technology and had a successful release to market. Bruce Karsten, 48 years experience, power electronics, everything from RF to heavy-duty transformers. We're actually implementing his dream, which is bipolar junction transistors. Now, silicon carbide provided benefits that he didn't know about because the technology wasn't mature 5, 10, 20 years ago. Bruce has said he'll work for no salary and he'll pay his own expenses just to see this technology come to market and make a big impact, okay? So I learned to be a fanatic about BJTs. The rest of the team have been fanatical for many years, and silicon carbide is the secret sauce that enables a whole range of benefits both in space and on this planet. Bert Allen has got 40 years fab experience, and I should have said earlier, the 3 key ingredients are 1, the materials quality, 2, the manufacturing technology, and 3, is the device design, and we add value in all 3 of those. We've already started discussing second source on the manufacturing side because while we have experience, Bert has tremendous experience in very high volume manufacturing, at the same time, we don't propose to raise hundreds of millions of dollars to set up high volume manufacturing. We've started talking with partners. We will work with partners. This is kind of an overview. I didn't list all of our combined experience, but as you can see, we've worked with or for large companies. My experience with analog devices, frankly, is buying DSPs for leading edge systems and then having them implemented in image and signal processing systems. Sam has actually worked for analog devices as a design engineer and a manager. As you can see, we've worked in a lot of different sectors, and I apologize on the kerning. You can see that there's some, in the middle column, there's some kerning issues, so I couldn't get it all to line up properly late last night. And then this is some of the recent companies we've worked with in terms of sales and account management. So we do have a fairly good outreach, and our initial outreach really is to both the main NASA contractors, Rockwell, Raytheon, Lockheed Martin, and so forth, because we expect to most likely sell either directly to the main contractors or to their subcontractors who are working on advanced electrical power systems. I mean, we're gonna go to our customer is not the end user. It may not be the main contractor. And this is our founding science advisory board. Dr. Michael Östling worked with Bo Hammerlin. They started the first BJT company in the world in silicon carbide. They sold it to Fairchild. So Dr. Östling is both the first investor in our startup. He's providing non-dilutive funding. And last but not least, he's got tremendous experience in bipolar junction transistors, 300 peer-reviewed pubs. He's got global prominence and recognition in the wide bandgap SiC community, and Bo has known him and worked with him for the last 15 years. Dr. Stephen Winston I met through Lockheed Martin a couple of decades ago. Steve is helping us in terms of relationships. He consults at pretty top levels, General Atomics, General Electric, Raytheon, Rockwell, Lockheed Martin, and so forth. So he really is an entry knowing where the people are that we should be talking to. And Dr. Agarwal also has a very strong, he was responsible for commercializing of SiC products for Cree. Subsequently, he went and helped launch the DOE's Power America initiative, which is the main driver for creating a wide bandgap infrastructure and community in the United States. And currently, he recently joined Ohio State University, where he's setting up a test lab for packaging and testing in the 3.3 to 50 kilowatt range. As I mentioned, we're probably going to be, for the next 3 to 5 years, in the 4.5 to 15 kilovolt range, anywhere from 10 to 50 amps in that high kilovolt range. And then we're also, but if our customer wants a high current, low voltage, happy to provide it. So we're high voltage and or high current. It's the customer drives what we develop, design, and sell. And here's our contact information. I'm happy to answer any questions. I've gotten really excited about, I love NASA. I'd love to have our stuff in on the lunar gateway, designed into the power systems, power beaming on the moon. I still read a lot of science fiction in my copious spare time, usually on airplanes. And then last but not least, we think we can provide pretty immediate value in low Earth orbit also. And thank you very much for listening. I had a tremendous experience. Thank you, Kira. Kira gave me a lot of advice. The summation was, do you want the money, yes or no? If you want the money, do it my way. And I said, hey, you're the boss, okay? And Kelly really had the patience to go through my presentation and remove everything that looked remotely technical. So we do have a whole different slide set, which is all the technology you always want to know about silicon carbide, but you're afraid to ask. And thank you again for your time and for listening. And I'm happy to answer any questions. And on deep technical, I'm going to punt to the two people of our team who are here, and we'll be happy to respond at any depth or length at the impact tables. Please.
So one question, you talked about the rad hard testing that you have done. How much additional testing would you need to demonstrate space radiation environments, or how much, what do you have to do there?
So there's three elements. There's the actual chip itself, the semiconductor, there's the circuit, and there's the power module. And obviously you can do rad hard on all three. On the chip testing, right now we're thinking of using the old Linear Tech Analog Devices facility in Silicon Valley. We are talking with other sources, but that's the most likely today. And we try to second and third source everything that we need from outside vendors because we just don't know at this point which one we'll go with. But Analog Devices is very interested in silicon carbide and BJTs in particular. So we may even end up with some sort of a more long-term business relationship. But the answer is until we have the chips that we're designing for the customers, right now we're in simulation and layout. We're hoping to start tape out in September. So get at least one run done this year. We think 3 runs should get us to what we would call a pre-production prototype. And it's on the pre-production prototype we'd start the radiation testing. And I'm not familiar with, is that something you can get done in a month or 3 months, you know? Same thing with temperature testing. I mean, are you doing continuous heat? Are you pulsing? You know, there's lots of different ways you can do testing. I know that much. So I think it's important to work with the best in the field and have them tell us. But we need to have the real customer chip. I mean, testing our prototype chips does nothing. I mean, we need to test the real chip. And then the circuit and the system design, we're going to work with the customer. We believe that our device physicist and our IC designer and our circuits and systems, really world-class guru. There's no other way to, I mean, in my opinion, he knows as much as any human being can really know. EMI, parasitics, you name it. And he does give technical presentations at technical conferences or conduct workshops or symposiums. And he'll tell you he's still learning. You know, you can't stop learning. So that's a very long answer to the, but we expect to be testing the chips within 1 year. And I suspect our customers will also want to independently test, at least for space applications. And I honestly can't tell you how long that testing may take. So that's my answer.
So you mentioned, so I'm also a big fan of bipolar transistors, but you mentioned that some advances have occurred in the last few years. Is that, so the problem with silicon carbide and bipolar transistors was the movement of the basal plane defects, and having minority carrier devices was difficult in silicon carbide. Has this been adequately addressed in the last few years? Is that
it's been adequately addressed and in prototyping at the materials. The materials are solid, no question about it. We can go to LC, Norstel. There are a number of companies that can provide substrate wafers. There are several companies. We have 2 identified so far that we could work with. These are all in Sweden, by the way. As I mentioned, KTH Institute and Sweden, the Swedish government decided in 1980 that wide bandgap was going to be one of the 2 areas. The other one's personalized medicine. So there's a reason you can go to China, India, you name it, and you see people from Sweden, well, sometimes Norway or Denmark, but they went to KTH Institute, and they're the ones who are doing the technology stuff. So basal plane dislocation, Bo Hemmerland can address it because he's really, one of his businesses makes the epitaxial reactors that let you lay down the crystal structures, which then in turn do not show. Now, if you're going to do a trench MOSFET, you're going to have issues with basal plane dislocation. With BJTs, we don't do trench MOSFETs. So the device structure is important, the manufacturing process, and of course, the substrate wafer. You need the best substrate wafers. A rough comparison, the best substrate wafers, quantity 25, are running around $850. The commercial ones are running around $650. So you got a price premium. That's come down in the last 2 years from like $2,000 to $850, and we think that trend line is going to continue for a while. So when we look at the manufacturing materials and materials manufacturing and device structure, we can see 1 order of magnitude decrease in cost in the next 5 years, and then a 2nd order of magnitude decrease in the following 5 years. But the short answer is yes, that problem has been resolved, but I would prefer you discuss it with Bo, and he can give you any level of technical detail that you would need.
Okay, excellent. The other question I have is driving these bipolar.
Sam Ochi, who's the other gentleman here, is
that's
a
okay.
world expert in driving.
That's
yes?
fine, but is that going to be a silicon technology or a silicon carbide driver technology?
Initially, we believe we can use commercial off-the-shelf rad-hard devices for space, but eventually it will be silicon carbide, but not initially. We're trying to. We only want to bite off as much as we can chew. That's the bottom line, and we got to get feasibility prototypes into customer hands quickly. We've got to get product to market quickly if we're going to make any impact at all in the next 5 years.
Right. And my last question is, you mentioned that the MOSFET, silicon carbide MOSFET, would fail in radiation.
No, I'm sorry. IGBTs fail.
Oh, I'm sorry.
IGBT.
fail because they have a gate oxide.
Right, and you get a single collision event at a few.
You also have a gate. You also have an oxide to passivate. The
yeah, AL203, sir.
No, I said you also have a dielectric that you have to passivate the base.
I'm gonna punt that to Sam and to Bo Hammerland. You have to understand, I have 8 years University of Chicago social and economic history, and I feel very strong in that area.
Okay.
Okay, and I've got an MBA in accounting, so I can look at a balance sheet or income statement or do product costing and put the costing tag on every one coming off the lines, or barcode, I guess is what they do these days. But it's not my area of competence. But I do know how to focus, and I do know how to make a business strategy work for a startup. I've had 6 startups. 3 were one was quite successful, 2 reasonably successful, but now this was in the 70s, okay? Then the next 3, I lost my shirt, we got a great education, and then I decided being a consultant was a much lower risk strategy. But I've been looking since about since 1990, I've been looking for a project where I could help build a company and make an impact, and this is it, okay? And that's why I'm doing it. And we started out looking at IGBTs, and then we slowly came to the conclusion that solving the basal plane dislocation and the driver issues would enable us to commercialize BJTs. And we believe that, and we have the evidence for that. But Sam can talk to you about drivers at a level of detail that I've seen 20 or 30 circuit designs so far. And to be honest, I'm right now in electronics engineering 101. I kind of know what a diode does. I'm solid on diodes. Okay.
Well, that's excellent.
Thank you.
If you understand the PN junction, you have.
Yes. Yeah. Well, I have to, because we're going to make PN junctions, but that's once again a downstream product. We can use commercial off-the-shelf silicon carbide PN junctions. They're available today. Please.
Yeah, I can address the 2 questions that we had. One was about basal plane dislocations.
Yeah, but can we do it the impact table, because we do have a time? Well, okay, I'm sorry. Go ahead.
I was recommended to take it right now.
Okay, go ahead.
And
sorry.
Basal plane dislocation is basically solved today, and we have a special supplier of wafer material, and they are basal plane dislocation free, and also reduced other types of dislocation with orders of magnitude, actually. And the second question was
drivers.
Why
don't you let Sam talk about drivers?
One other technical question about.
Was the base emitter dielectric?
The dielectric. Sorry.
You still have to passivate the base emitter junction.
Yeah, but we don't have a gate on top. So the problem is with the gate, silicon dioxide, silicon carbide, and you introduce a lot of deep levels in there, which can. When you increase the temperature or lower the temperature, you have different grade of fillings in levels there.
Yeah, different coefficient expansion.
Okay, I can answer a little bit of the issues regarding oxidation or oxides, especially passivation over the device. Now, it turns out, my understanding, and again, I'm not a process engineer, but what you do is you use nitride. Nitride is a lot more resistant to radiation than thermal oxide, which is silicon dioxide. And silicon dioxide is the key problem with radiation, and especially single event faults. What happens is that you have a charged particle or a particle that goes right through, and it'll go right through silicon dioxide. Nitride is a lot more resistant to that. And also, even if it does go through, what happens is that the areas where it gets affected are in what I would call the areas where the device is not really doing anything. It's not in the active region of operation. The key sensitivity is in the reverse biased, or it's between the base and the collector, that region. That's where you have to sustain the high voltages, high currents, high current densities, and so on. I don't know if I answered the questions. Okay.
Two other additional things there. The most transistor, you can't use it for very high temperatures. I think the limit is like 185 degrees C. The bipolar junction transistor, we proved that a number of years ago. We went all the way up to 550 degrees centigrade. So that's a big difference. And also another thing that you asked about is the lifetime carriers. So we have a process where we actually do process the drift layer. The drift layer in the transistor could be like 200 micron, but with a fairly easy way to process this. Still some trade secrets. So we can actually choose how long lifetime we want to have. So it's not too short and not too long.
So
I don't know if there's any other questions.
I have one question.
Yes, please.
So for terrestrial applications where radiation hardness is not important, is the main differentiator for this technology then the temperature capability? I understand it's more efficient and lower cost, but I'm trying to get a sense
if you
of the
put
magnitude.
if you put let's say two chips in a series, one's 99% efficient and one's 96.5. If you run the numbers very quickly, 96.5 gives you around 80% efficiency. 99%, you run the numbers, I think you're around 97. I'm doing it in my head, so that's more or less right. So that's quite a big difference. If I remember correctly, it's a 13. If you put 6 chips in a series for voltage, for example, you got about somewhere around, say, 14% plus or minus 1% difference in efficiency.
Okay.
So, I mean, you prefer to be more efficient, right? If you could make the entire national grid 14% more efficient, that's a big number. I mean, it's high value. And then the other advantage is BJTs, and this is a technical thing that I can't explain to you because I'm not technical, but I've been told by Bruce Karsten, who is our circuits CTO. We have 2 CTOs, one for SiC semiconductors and one for circuits and systems. So he's designed transformers, windings. He's got 3 recent US patents. If you want to do a solid-state transformer, it's going to be hard to get around the patents, and he's willing to assign them to our company if and when we want to get in the solids. If you have a customer for SSTs. So for SSTs, he believes the BJT is a key enabler because you really do want it more. You want more efficient devices. You want them to be smaller. You want them to be lighter weight, and you really want them to last longer in the field. And thermal degradation is an issue. Now, there's some pretty nice new technology that I've seen out of the Freedom Consortium, out of NCSU. We have talked, and we will be partnering with both Power America and with Freedom Consortium. They've got their annual meeting August 23rd, 24th, if I remember correctly, so we'll be there. It's a money issue right now. I mean, it's $5,000 for the Freedom and $10,000 for Power America, so right now we're self-funded, paying all our own expenses. And
Bo,
so,
I think you've got one more question here.
okay,
If I
sorry.
can just answer one thing, which is very important. Switching speed can go up by a factor of 10 to 20 because switching losses is very small, and when switching speed goes up, you can shrink down capacitors and inductors to about 75% of the original volume that you use for silicon. So that's one.
But at these voltages, you're not going to switch very fast. So you're
No, but
not.
faster
So the conduction losses are more important than switching losses.
Well,
these
yeah, that
voltages.
is true, except, again, it's still faster than what you can
Of
do with
course,
silicon.
yeah.
And in fact, this is also true with respect to silicon carbide MOSFETs. Okay.
Yeah, we get that.
So that's time, and I think the impact table discussions are going to be interesting.
Thank you very much for your time. Appreciate it, giving us the full time.